So our next speaker is Lionel Parreaux, a joint work with Christophe Koch, both from EPFL, and he's going to talk about comprehending monoids with class. I think it's very interesting. Let's wait a second until it's stand up.
Press the button.
Yes, perfect.
Yep.
Right.
Oh, no, second. Okay, so if you have any questions, please interrupt me, because if something is not clear, it's just that I'm not making a good job. Right. So, in the beginning, there was set comprehension, and it was very flexible. It was, in fact, too flexible, and so then there was restricted set comprehension, which was much better, and that's right. And it was in fact so useful that people wanted to use it in programming, and so they started using list comprehensions that you could use to write actual programs. And so in this comprehension syntax, you iterate over pre-existing sets. Now, then we were like, okay, so, but why list, why not any monad? And then there came monad comprehension, and but then people thought that it should be written like C. Anyway, so in this talk I'm going to talk about comprehensions in order to represent queries as in database queries in functional programming languages. So it's been well known that comprehensions are a neat way to represent SQL-like expressions, such as this expression. I think everyone is familiar with either SQL or these comprehensions here. So this is just an example. And then we realized that this was a bit too restrictive, so we need to extend the comprehension syntax in order to have things that SQL has, such as grouping and ordering. Right. And in parallel to this, there's also, in the context of object-oriented query languages, which have nothing to do with object-oriented programming, but that was the buzzword at the time. So in the context of object-oriented query languages came monoid comprehension instead of monad comprehension by Figueras in 1994. And in this talk, oops. So the idea is that I think we haven't paid enough attention to that alternative form of comprehension, and it deserves more attention in this community. So I'm going to explore what monoids give us when we want to represent queries. I'm going to talk about the monoid comprehension calculus introduced by Figueras and generalize it a little, and talk about how to embed it in actual programming languages. So, first of all, let's remember what's the semantics of list comprehension. Here's an example of list comprehension that iterates over two lists, x's and y's, and filters the iteration using function f and produces values using function g. And so the semantics is conceptually in terms of this goes to concat map, which maps a function over the lists, and then concatenates the results. So assuming the function creates lists, and so you end up with a list of lists that you concatenate. Right, and this is the way you would write it if you want to express it in terms of monad comprehension. But it's the same idea. And so one of the first things to notice is that in monad comprehension, everything here, x, y, the result of the comprehension has to be in the same monad that is fixed. So you cannot iterate over different sets of things and build up a different type of monad without doing explicit conversions. So what about the semantics of monoid comprehension? In monoid comprehension, the main difference is that instead of concat map, we use fold map. And also notice that we don't wrap the results in anything. We just take the result as it is and aggregate it with the current results using the monoid operation. So fold map has this signature. It takes anything that can be folded. It takes a function that turns the elements that is foldable into a monoid, and then it aggregates all the monoids of the elements. And so notice that in this comprehension syntax, you have no homogeneity requirement. X as Y as can be any foldable. The result of the aggregation can be any monoid. It doesn't even have to be a collection or foldable. So a way to see it is that if I parameterize the query with all its three variables, well, we have this very general type that has three class parameters. It shows us that we really don't require homogeneity. And here's an example of iterating over a list 1 to 3 and a set of strings, and then I add the elements from the list with the length of the elements from the set, and I compute the sum of this whole thing by wrapping this into the sum new type, which is just used in order to say use the sum instance for integer monoids. Is that clear? Okay. So, okay, as a side note, it's very straightforward to encode monoid comprehension in list comprehension. You just have to wrap the list comprehension in fold, and you have to wrap the source collections in the two lists in order to convert the foldable into a list. But one of the problems is that you're creating a lot of useless list, intermediate list representations. In this particular case, notice that we're really building the Cartesian product of x's and y's, and only then filtering it, and then only folding it. So it's kind of wasteful, and it's a bit nicer to just directly use a monoid comprehension. So let's talk about grouping. Grouping does not fit very well in monad comprehension without doing any extension. So we need to add something to monad comprehension in order to express grouping conveniently. And this is the way it's been done. But the thing is, in monoid comprehension, you can actually do grouping just fine, directly, without any extension. And this works by simply aggregating a map. Because when the elements of the map, when the values of the map are semi-grouped, then the map is a monoid, and then you can use it as the result of a monoid comprehension. And so this group by method, all it does is put its argument as the value and the key of a singleton map, and aggregate this into the final map that represents the grouped values, right? And what you group doesn't even have to be a collection, of course. So here we're computing the sum of the balances of accounts, of bank accounts, grouped by the name of the holder of the account. So we're making the sum. we're wrapping the balance into a sum to express that we want to make the sum for each order, right? And so it just works out fine. Another thing is, so let's look at what it the sugars do in monad comprehension. This grouping construct in monad comprehension, the sugars into something quite intricate. It has a lot of intermediate lists. In particular, it constructs a list of tuple, and then it traverses this list twice in order to get the left elements, do something with them, get the right element, do something with them. And so it's not very elegant, but with a monoid comprehension, this just desugars to a single full number, right? So using fusion, maybe some of the intermediate lists would be removed. In that case, I'm not sure it would work, but it's a bit nicer if you just have the right thing from the start. So let's talk about the monoid comprehension calculus that Figueres introduced to talk about these monoid comprehensions. So the original formulation has this form where n is the merge of the monoid that you want to use as a result monoid of the comprehension, and it's baked in a set of predefined monoids. So in this approach, you don't have things like group by because it's not predefined in the finite set of predefined monoids. So it can be list concatenation, it can be union, set union, bag union, etc. Integer addition. Okay, and the semantics of these comprehensions is given in terms of monoid homomorphisms, and this means that not all comprehensions are valid. And here's an example of an invalid comprehension. If you try to iterate over a list and then over a set, and then you try to turn this into a list, it's invalid because the list remembers the order in which you aggregated the elements, but the order in which you're supposed to iterate over a set is not specified, so you shouldn't be able to observe it. We really want to give the implementation of the query and of the set representations as much freedom as they can have in order to be efficiently implemented. So in general, there's these two properties, commutativity and independence. And so if you, for example, they form a lattice, and if you, for example, iterate over collections that are commutative, such as bag, then the result monoid of the comprehension should be also commutative. And this could be sum, for example. Or you could aggregate the elements of the bag into a set, but you cannot aggregate the elements of the set into a bag because bag is not idempotent, meaning adding the same element several times doesn't result in the same bag. So this is already useful, but we can actually extend this in other useful ways for programming, which is what we did. For example, we can add a notion of non-empty collections. The thing is that if you iterate on non-empty collections, then what you have doesn't need to be a monoid comprehension. It can be a semi-group comprehension because you don't need a zero element if the source collections are non-empty. Another thing, so here's an example. If you assume that some excess is non-empty, and then you do a count of whatever of the number of elements in excess, you want to have you want to propagate the information that count is going to be non-zero, and the type of count is non-zero nat. This has a semi-group instance, but not a monoid instance, because there's no zero element in non-zero of nat. And so this works out fine thanks to this generalization.
This example just gives a spec. Like what is the type of what comes back? Is it like a set of one?
So the type is annotated here.
The
type is annotated here as non-zero of nat. Non-zero is a new type wrapper to input some information about the result that you have.
But here you didn't get merged the one counts, right? It's still a
so
set
for each element, you create a count of one, and then you aggregate these counts using the semi-group instance of count. The semi-group instance of non-zero nat.
Implicit merge always.
Yeah, so that's the main.
It's going okay.
That's the main difference between the monoid comprehension calculus as presented by Figueras, where you explicitly say the merge operation and our embedding in functional programming languages, which relies on type class resolution, which is much more flexible because the instances are resolved implicitly, and you can use new types to add more information to the comprehensions.
Right.
Okay.
And that's why I called it net.
Could it what?
That's why I called it net instead of eight.
Yes.
It's another way.
So here's another example of something we want to do. If access is not known to be non-empty, we don't want. We still would like to aggregate it, and we don't want to use the monoid instance that would be normally associated with a semi-group that doesn't have a monoid instance, which would be maybe of this semi-group. And so even though count aggregates non-empty NATs, we would like to get NAT as a result in case access is not empty. And so we have this notion of associated canonical monoid to each semi-group. So for example, the canonical monoid for associated with non-zero NAT is NAT. Associated with non-empty list of A is list of A. Max of NAT is already a monoid as well as a semi-group, so it doesn't have to change. And our goal is to make the comprehension type system infer this as appropriate, depending on the types of what's in the comprehension. And so here's a slightly bigger example where, so I'm not going to go over it in much details, but it aggregates several things in parallel. It aggregates the count of some words irrespective of the case, and as well as the maximum length of the words insofar, and iterating from a list of file names and a stream of characters or whatever. This gives us a nice precise type for the query. Okay. In particular, notice that the map, for the map to be a monoid, it's insufficient for its value type to be a semi-group, and so we end up with a map of string non-zero net, because you cannot have a zero element as the value of the map, because otherwise the key would just not be there. Okay. So how do we embed it in a programming language? We chose Scala to do our embedding because it already has a for comprehension syntax that can be repurposed at will. So it doesn't have to be monadic as opposed to comprehension in Haskell. Also, something we need in order to get the most precise types depending on the collections that we iterate on is a way to have overlapping overloading and to pick the most specific one depending on the types that are involved. And Scala is already functional and type class oriented, so we have nice libraries of monoids, homogeneous monoids, etc. And this is the example rewritten in the Scala syntax, which uses the for comprehension. The only difference is that the yielded element is at the end instead of the beginning. Okay. So we use priorities, which is it. And as a conclusion, I think that for expressing queries, as in database queries, monoid comprehension can have many advantages over monad comprehension. It's more flexible, as you can aggregate different kinds of stuff without conversions and fold directly without intermediate collections. There's a more straightforward desugaring, and you don't need to extend the comprehension syntax in order to have grouping. It's more efficient because also we know how to optimize it, because there's been a lot of work into optimizing the monoid comprehension calculus, and because it doesn't create all these intermediate collections. And it's safer because we can statically encode restrictions at compile time on the kind of queries that you can express. For example, in our Scala embedding, again, you cannot iterate over a set and try to aggregate results in the list, because that would be observing the iteration order of a set which isn't specified. And with break optimization. Okay. That's it. Questions?
So would you use this comprehension syntax purely sort of style? Not style, but I mean, you could write all of this in a sort of combinatorial way.
Yeah, so the comprehension syntax is both useful for users to have neat syntax that look like SQL, but also as an internal representation for optimization, it turns out. And so if you look at the way monolith comprehension calculus is optimized internally, it uses rewritings on this comprehension syntax.
The actual implementation of this in Scala or other languages, how do you enforce that the set can't be iterated over, or that certain things are commutative, or I don't know?
So the set has an instance of the typecast instance that says that it produces elements in an unspecified order, and in order to use this in a for comprehension, the implementation, the overloaded implementation that is picked for this set is going to require that the monoid be commutative and independent. So it always picks the most appropriate implementation of the comprehension implicitly, and at the end it requires the right monoid type. So we just have a bunch of cases for all the combinations of properties.
I have a related question. So early in the slide, in 1, we type non-zero net.
Right.
So what if I write 0, we type non-zero net?
Yes, so this is for the library designer. It's the library designer's burden to make sure that their new types are safe in the sense that it hides the ways to construct the wrong elements.
Yes, I
using
put Y, right?
Yes, so
then things would go
of course
kind of somewhat wrong, maybe.
Of course, yes. So similarly, if you implement commutative monoid for something that is not commutative, it's exactly the same problem. You could lie.
Yes.
It's not Idris.
No, that's fine. And I have another quick one. Well, something other question. Yes, let's.
I just wanted to ask: is it only are commutativity and idempotency the only things you want to be able to preserve like this?
So it's not the only thing. We extended these two things with two properties, which is non-emptiness and finiteness. So we have a notion of lazy monoids. For example, integer in Pascal is not lazy, so you cannot try to aggregate and ensure while iterating over a potentially infinite collection. So yeah, we have these two other things, but maybe there's more interesting things.
Yeah, quick question. So you mentioned that I don't know how the type class mechanism works in Scala. I'm not familiar with Pascal, but you mentioned it's a good thing to have type classes. In my case, though, I sometimes whenever I have too many type classes and the resolution is under the hood, it's very confusing what actually happens, especially nowadays with the folder with reversible, and for instance, tuples having non-standard instances. Do you think this could actually produce very confusing results?
Yeah, as you add more interaction and more inference, you get weirder results. Weirder errors. That's a good point. Yeah.
Sometimes we can actually bug this thing.
Yeah, that's right. It's the big problem with type classes. In Scala, we have a mechanism to customize error messages depending on which implicit is not found. So it can alleviate some of these problems, but if you go too far, then yeah, you get crazy errors.
All right, let's thank the speaker.